Okay. So this is what physicists are made for. This is the next example. If you are a physicist, I expect that you will do this many times, and the multitudes will love you for it. So it's an inclined plane with a box on the inclined plane. The box has a mass m, little m, and the inclined plane has a mass of large m. The total length of the, we'll move to saying wedge instead of plane. The whole wedge has a length of L along its hypotenuse. And then we're gonna write two generalized coordinates that we're gonna be using. One is right here and one is right here. But we do have some issues with reference frames, stuff that we're gonna have to tackle when we're dealing with this one. This is a little bit more of a little bit more complicated of a system. We're having these different coordinate systems now, and we're gonna have to be very careful about the way that we go about it. Inclined planes in quantum computing, yep. Okay, so the two generalized coordinates from the pictures that we're going to be using are Q1 and Q2. Those are the two generalized coordinates. Okay, so let's set up the system, right? Both there's a block and a wedge. They're both free to slide with negligible friction, right? We're not going to worry too much about friction. If we release the block mass little m, okay, at the top of the wedge, how long does it take to get to the bottom of the slope? So if we and they're both free to move. So as we release the block little m on top, the wedge is going to slide this way. The m block is going to slide down the wedge. How do we do this? Right? A bit more of a complicated system, or is it? Yeah, it's kind of complicated. So let's start it. The kinetic energy of the wedge is actually not too bad. So the kinetic energy of the wedge is just going to be 1/2 m q dot squared. Q dot 2 squared. There you go. But then we have to talk about the block on top of the wedge, and the motion relative to the wedge is Q dot is Q1 dot, right? So the motion relative to the wedge is Q1 dot. As it slides down, Q1's changing. Wait, sorry, hold on. Right? So, but that's a different reference frame than as it's changing in reference to the table, so we have to figure that out. So relative to the table, the velocity has two components, Vx and Vy. And what are those two coordinates? Well, we have Q1 dot times cosine of alpha. I forgot to draw alpha. Alpha is this angle right here. So for those of you who wanted alpha, there it is. Plus Q2 dot. And then our y, so we have the x, so basically what this is the velocity of the x component, which would be that way, but also the velocity of Q2, because as it slides, we're going to gain that velocity as well. And then the other form is Q1, or I'm sorry, Vy is Q1 dot sine of alpha. So the kinetic energy of the little block is just going to be, again, we want that 1/2 mv squared. So we get 1/2 m, and then we have Vx squared plus Vy squared, right, to get that V squared. And what is it? Well, we can then substitute these in, and we'll use the identity of the old, cosine squared plus sine squared is equal to 1, and we get 1/2 m times Q1 dot squared plus Q2 dot squared plus Q1, 2 Q1 dot Q2 dot cosine alpha. Okay? So now, can we write the total kinetic energy? Let's write we can write the total kinetic energy. It's just adding the two kinetic energies of the wedge and the little block. But let's write the potential first, and then we can just write the whole Lagrangian down, right? The potential is relatively straightforward, right? Because we only have the potential due to the little block. The wedge is already on the table, So we don't have to worry about that potential. Instead, we just have the potential energy of the little block, which is minus mg q1 sine alpha. Okay? So now we can write the entire Lagrangian. That'll be a long one. And it's just going to be t minus u, which is equal to 1/2 big M plus little m times q2 dot squared plus 1/2 little m times q1 dot squared plus 2 q1 dot q2 dot cosine alpha plus mg q1 sine of alpha. There we go. So that's the whole Lagrangian. Not too bad when we get to our derivatives or our equations of motions, right? We only have two equations of motion because we only have two generalized coordinates. So two generalized coordinates. We'll start with q1, or I'm sorry, we'll start with q2 because that's relatively straightforward. Again, this has no q2 in it. It has a q2 dot, but it has no q2. So if we take, let's write out the Lagrange equation of motion really quickly. There we are. So the left-hand side of the equation is going to be 0. And the right-hand side of the equation is going to have some stuff because there is some q2s in it. And we have d dt. So the derivative with respect to time of big M q2 dot, plus little m times q2 dot plus q1 dot cosine alpha. Hopefully you guys can see that still. Ooh, look at that. We are right on the edge. And then we can keep going with that. And, well, everything in there, the only difference really with that is all of the q2 dots turn into q2 double dots, right? And we also know that this is equal to a constant then, right? Who cares what kind of constant, right, Tyrion? But that term right there is equal to a constant. Make it fit. Okay, and then let's see here. So we can do Q1 now, which is a little bit more complicated because there are both Q1 in the Lagrangian as well as Q1 dot.
I still can't over the fact you renamed phi.
That's the only thing I could think of. It made sense to do. Can you move the board down a bit, please? Sure, absolutely. Hold on. No. The answer is no. But good to see you, boring math professor. As always, good to see you. Now this one's a little bit more complicated, like I said, because we have Q1 and Q1 dot. So what do we get for this one? Oh, what do we get? What do we get? This one's mg sine of alpha. There's only one Q1 in this entire thing. It's right here. So we only just get mg sine of alpha. And that is equal to m times q1 double dot plus q2 double dot. Cosine alpha. There we go. So now we have this thing where we have q2 here, and we can solve this for q2 and then plug it in here. We have q2, and these are all q2 double dots, excuse me. q2 double dot equals m over m plus little m q1 double dot cosine alpha. There we go. I know you are an English professor. Okay. And then we can go ahead and plug that in for here and solve for q1 double dot. Why do we want to solve for q1 double dot? Let's find it. q1 double dot is equal to Oh, I forgot the equal signs in the notes. That's not that bad. Wrote a bunch of notes. Forgetting one equal sign is not bad. G sine alpha divided by 1 minus m cosine squared alpha divided by big M plus little m. Now, this is relatively straightforward. This is a good result to have. Let's write it down up here a little bit, and then let's talk about it. So let's keep our picture up here. We solved all of what we needed, but we have some interesting things that happen with this. Right, we wanted to find the acceleration q1 double dot is equal to g sine alpha divided by 1 minus little m cosine squared alpha divided by big M plus little m. Now, so what do we get with this though? This is kind of an interesting result, right? We wanted to find the time it took. Well, we can write the time it took basically by saying how far it's going to go is equal to 1/2 times the acceleration q1 double dot times t squared, right? That's old kinematics for you, right? Good old kinematics. And then we can solve for the time. The time is going to equal the square root of 2 times L divided by q1 double dot. q1 double dot consisting of all of these things that we already know. So, with these results, let's talk about the system a little bit, right? What happens? So this is the time it takes to get down the inclined plane. Now, what happens with our acceleration if we start modifying some of these things, right? So what happens if we modify some of these things? Like, what if we take this alpha and set it to 90, right? That means that this comes up to here, and now our mass is going down the plane like that, right? So we set alpha to 90. Well, let's run that really quick. Let's set alpha to 90. Alpha goes to 90, that means sine of alpha goes to 1. Cosine squared of alpha goes to 0. This term goes away, right? And we get q1 double dot is equal to none other than the acceleration due to gravity. Hey-oh, that's a cool result, right? How about this? How about what if we take this mass of the inclined plane and send it to infinity? M goes to infinity, that means this term goes to 0, and we just get g sine alpha. G sine alpha would be the same acceleration as if the block, or if the wedge didn't move. Mass goes to infinity, mass goes to infinity, the block basically doesn't move, and then the acceleration down the plane would be just like a fixed plane. Just as I will spend up to 5 notations to make the following changes. D goes to lowercase delta, your coordinate Q goes to lowercase zeta. The derivatives of the coordinates, lowercase, any masses, capitals. Okay, let's do it. I'm only doing it with what's on the boards. Once we go to the next notation, I gotta change it back. Because it's a different problem. I think all the notation is gonna change anyways. We never use momentum conservation. Actually, yes. This right here, if you're interested in Pretz, this is momentum conservation right there. I'll wait for the next problem. So you're gonna wait till well, the next problem's the last problem. So when I'm all done with the next problem, you can feel free to change everything you want. And you don't even have to tell me what symbols are. I'll do my best to try them. Okay? So that's what happens. This is just an interesting result, right? If it's a if we take the plane, take 90, it's a free fall. G, right? If we take the wedge, make it incredibly massive, it doesn't slide, we get the normal, what we'd get in like introductory physics when the mass does not move. Cool. Okay, we got one more example to do. We have quite a bit of stuff for today. But it's a good day. I like the examples. They really like kind of shed a lot of light on the stuff that we've done up to this point. Last example is a bead on a spinning wire Why did I write hook? It's not a wire hook, is it? I thought it was just a spinning wire. Hoop, hoop, not hook. Hoop. This guy. Spinning wire hoop. So now we have, again, so let's draw a picture. We have our axes, we have our wire hoop, we have a ball, a bead, ball, whatever. There's some radius r away. We can talk about the radius away from here. We'll call that rho. We are in spherical coordinates this time, I think. So let's start laying down stuff that we're in. Even you can't read that. Okay, I can. I just had to double check with the book because I wrote down the wrong word. It's not chicken scratch. Chicken scratch. Omega is the velocity. So we have a hoop and it's spinning and there's a bead on it. Okay, and we have to find the equilibrium spots of a bead. So for example, right, what spots are we going to spin it, the hoop that is, such that the bead won't be sliding up or down, right? So maybe just the Lagrangian. See, when it's over, then we'll just cut the YouTube video stuff, and then you can change everything if you want. So the constant angular velocity, again, we're doing constant angular velocity is equal to omega, right? Angular velocity being how fast it's rotating, okay? And we're supposed to find the equilibrium points and explain their locations in terms of statics and the centrifugal force, m omega squared rho. So for the kinetic energy, following our normal prescription, we want the kinetic energy, mv squared. We do need to talk about it in generalized coordinates. Is there a way we can describe it such that it's in one single generalized coordinates, and there is that generalized coordinate being theta? Yeah, I really like this problem. This generalized, I actually remember this problem from my class taking it a couple of years ago, and I really enjoyed it. By a couple, I think it's like 4 or 5 now. Ugh. And V has 2 different forms. We can talk about the bead as it slides up and down. So in a stationary plane, right? So if we had the hoop standing still and the bead slides up and down, that's a tangential to the hoop. So let's see, let's draw. Here we'll have some theta, right? And then, can we describe this omega force, or the velocity of the bead as it spins around this way? And we can do that as well. So there's basically 2 different tangential velocities, right? One in each of the angles. There's this angle going this way, and then there's this angle going this way. And each of those is going to have a tangential velocity. The first one, this one going up and down, is we're back to our r theta dot, right? That's the one velocity. I'm not going to go too involved into this and like have more labels and stuff. The other one's going to be omega rho, where rho is this spot right here. This is basically like saying how fast it's spinning in this direction. Again, this is just the same thing, radius times the angular velocity. And because now if you had this stationary here, it would be rotating around like this. The radius that's rotating is the rho. And then the angular velocity is that omega. And this is going to be equal to r sine theta omega. I'll put it out front. Whew. Let's just do it properly, I guess. Curse proper things. So we'll have omega rho is equal to rho r sine theta, where rho is just equal to r sine theta. Okay, so we have our 2 different velocities and our 2 different tangential velocities. So we can write down our kinetic energy in terms of those. 1/2 m. So again, we're rewriting the velocity. Now we're in one single generalized coordinate, which is really nice and makes this problem much faster. Plus, so it's theta squared plus omega squared sine squared theta. And we get two types of, so like I said, here's the tangential velocity, and here's in the one direction, and here's the other tangent in the one direction, and here's the tangential velocity in the other direction. Close that parenthesis. And then let's see, the potential is given again just by how high, how high this is. So we can evaluate there, and it's just going to be mg r1 minus cosine theta. As we change theta, can we change the potential energy? And of course we can. Just follows that formula. So what's the total Lagrangian then? The Lagrangian is then going to be 1/2 m large R squared times the quantity of theta dot squared plus omega squared sine squared
Looks to me that
theta
bead is really high.
minus mg r1 minus cosine theta. That bead is really high. It's not that high, okay? We're only talking about the bottom of here, okay? So it's fine. Now,
Wait, no. That is me.
you were setting yourself up. Come on. So of course the last thing we have to do now is solve for the equations of motion. The derivative of the Lagrangian with respect to theta. Oh, Justin's going to miss the best part of this, which was the poll that we had to do. We'll do it in Twitch chat. That way people can be anonymous in case people want a defect. Okay, so we have the derivative of the Lagrangian with respect to theta, and then also the derivative of the Lagrangian with respect to theta dot. So that's a little sloppy. And we can write what that is, and the left-hand side is m big R squared omega squared sine theta cosine theta. And the right, oh shoot, there's more, minus mg r sine theta. Whew. And then there's the other side of the equation, which is just m r theta double dot. I think that's supposed to be r squared theta double dot. Let me double check. It is r squared theta double dot. Very good. So this is the last equation of motion. Can we solve for theta double dot? Of course we can. Theta double dot is equal to omega squared cosine theta minus g over r times sine theta. Now, if we want equilibrium, what do we want? We want this theta double dot to be zero.
Welcome to the channel. Things get a little bit weird.
Bush Rush, thank you for the follow. Welcome to the channel. We'll have to wait. Okay, so we want this theta double dot to be equal to 0. That way there's no acceleration in this direction, and it stays stationary. And what are the two options for that? Well, we can set sine theta equal to 0. What are those two options? Sine theta equal to 0 is at pi and 0, right? So that way, if the bead is perfectly at the top of the center or perfectly at the bottom of the center, then it's not going to move at all when the hoop is rotating, right? There's no reason to. There's no force acting on it other than gravity, and everything else cancels out, and including the gravity has a normal force acting from the hoop that we're not worried about right now. Or else, it would fall off the hoop and come to the ground, which obviously we can't have that. So instead, what we have is it's spinning, and the bead is stationary perfectly at the top or at the bottom. Now, but those points are unstable, right? So there's some restoring force that makes the top unstable, but the bottom is stable. I think the bottom's a stable point. The top point is unstable because there's no restoring force to get it back to the top. So at any single slight deviation from the perfect top, it would slide down. Yeah, I think you still have to nudge it either way. But then what else is there? There's some other points. So we talked about sine theta. What about the rest of it, right? And it's true, we can talk about the other side. This could equal 0, but this could also equal 0. And instead we get cosine theta is equal to, let me go back to my notes, g over omega squared r. Now, of course, there's some constraint, right? Because the absolute value of cosine theta has to be less than or equal to 1. So that means that omega squared has to be less than or equal to g over r. So there are sufficiently fast spinning points when omega squared is equal to equal to or greater than g over r. And what are they? Well, theta, we just solve, plus or minus cosine inverse arc cosine, we'll call it, of g over omega squared r. Now, that means that there's 2 points, or several points, at the bottom of the hoop. There's one over on this side and one over on this side. That if you were to put the bead there, once you start spinning it, then the bead would be stationary, right? We have, that's the cool thing about this, is you can actually, and maybe we'll build one of these someday. We can actually build this apparatus where we have a hoop and a bead, and when we spin the bead, then the bead, with fast enough angular momentum or angular velocity, we can guarantee that the bead would stop at a stationary point along the hoop. Now, what does that mean? Again, at the bottom and the top of the hoop, when the hoop is spinning, the centrifugal force is 0, and then there's the cancellation between the two. I think if omega is fast enough, it will make the bottom point unstable too. Oh, sure. Yeah. I think it's when it's this, right? That makes sense. When it's this speed, then the bottom is unstable. Yeah. Okay. All right. Interesting. Yeah, I didn't really go over that part. I was probably planning on skipping that. I wasn't really gonna do the next one, but Justin really insisted, so maybe we'll do it next week. But let me finish this one. So when it's spinning slowly, then it can be resting at the top or the bottom, less than this. Whoa. So when it's spinning slow enough, there's no centrifugal force, and the top and the bottom is where the stable points are. There's no centrifugal force on the bead, right, that it feels if it's stationary at the bottom or the top. However, once you start spinning fast enough, then the bead starts to fight with gravity versus centrifugal force. Yes, it is time for an experiment. I think we need to build this one. We should definitely plan on building this one in the near future. And the centrifugal force acts on the bead. It's basically like if you were a fly on the bead, what would you experience? Well, you experience the centrifugal force in one direction and gravity in the other direction. Those are the two forces that make it obvious. Or that make it, not obvious, stable, stationary. Stationary points, there we go. Equilibrium. And we can establish all of those points based on this formula, okay? So now, like I said, if you were a fly sitting on the bead, you would experience two forces. You would experience centrifugal force, and you would experience, thank you, Jax, and you would experience the force due to gravity.